So we're going to continue from where we stopped. We lost 2 lecture times, so we'll try to catch up a little bit. So today we're going to continue the discussion on ER. To give you a quick recap of what we discussed in the first lecture, we said ER model is a data modeling tool for you to capture user requirements from user applications, right? And it consists of mainly 2 components. One is what we call entities, the other is what we call relationship. And the collection of the same type of entities form an entity set, and the collection of same type of relationships form a relationship set. And a relationship basically captures interactions between entities from either the same entity set or entities from different entity sets. And entities are used to describe real-world objects. Okay? Those are the things we said last time. And we stop right here with talking about how we capture this what we call participation constraints. So participation constraints refer to those type of business logic that require you to specify whether a particular object may have one or more interactions with object from the other side, from another entity set. Right? So to give you an example here, suppose I have 2 entity sets, the employees entity set and the department's entity set. And I want to capture 2 relationships between the 2. One is an employee works in a particular department. That obviously gives you a set of relationships, and the collection of those forms the relationship set at the bottom, which is the works in relationship set. At the same time, some employees, obviously not all employees, are managers for the corresponding departments. And that means there's another type of interaction between entities from these 2 entity sets. This example also illustrates to you that it is possible to have multiple different relationships for the same entity set. Right? So, having said that, that explains why we have another relationship set called managers. What's different though is not all employees are managers, obviously. Right? And furthermore, typically each department has only one manager, right? By common sense, right? Unless otherwise specified. So the question is, how do we capture such constraint? How do we capture such? So obviously there's a difference, right? So I'm gonna use the whiteboard to illustrate the difference between the 2. So this is the employee entity set, this is the department. Here I'm gonna just duplicate the same 2 entity sets, right? Employee and department. Okay. And here is, the works in relationship set. So for example, when I draw a line like this, that means employee 1 works for department A. Right? So let's say 1, 2, 3, 4, 5. I have 5 employees and department A, B, C. That's how I'm going to label that. So that line simply tells you employee 1 works for department A. At the same time, the same employee may work for multiple departments. And the same example goes to a university setting, right? The same student may double major in multiple departments. That happens all the time, right? So let's say employee 1 also works for department C. Okay? At the same time, this doesn't prevent another employee from working at either department A or department C, right? So it's possible that employee 3 also works at department A, but it doesn't say anything whether employee 3 should also work at department C, right? So actually, employee 3 may work at department B. So that's a typical setup, right? And this is what we call many-to-many constraint, many-to-many participation constraint. Why is that? Because if you look at any entity from the left-hand side, any entity from this side, an entity from the employee entity set may participate in many relationships with entities from the department entity set. So, meaning if you're looking at this side, any entity here may participate in many here is 2, right? Relationships with entities from the department side. That's why from this side is many. Similarly, if you stand at the department entity set and you look at any department entities, any department entity may take multiple employees who work in that department. In other words, any department entity may also participate multiple times in this relationship. So that's also many, right? Combine the two arguments, you derive this constraint that's called many-to-many mapping. Many-to-many mapping. Okay, any questions regarding this discussion here? So far so good? Okay, cool. Coming to this end, I'm going to duplicate, because remember, they are the same data set, right? So I'm going to duplicate the same data set. So I'm still going to have 5 employees and 3 departments. So this is same entity sets but different relationships. So for that purpose, I'm going to use a different color to indicate it's actually a different relationship. Okay? So when I draw a line like this, what does it mean? That means employee 1 is actually a manager for department A. If you are given a user requirement document which specifies that each department can only have 1 manager, but the same person can be managers of multiple departments, right? What that tells you is it is possible that employee 1 is also the manager of department C. That's okay, because you are allowed to be managers of multiple departments. However, if you are given a user specification that says each department has only 1 manager, that means you cannot have a relationship like that, connecting employee 3 to department A, given that you already have a relationship between employee 1 and department A. Why is that? Can someone tell me why is that? Why we cannot have the second line over here? Yes, go ahead.
Can we only have 1 manager per employee?
Per department, right? Yeah, that's because that's given in the specification. Each department can only have 1 manager. So if you were to have that second line, that would be a violation of that constraint. Okay? So this is not allowed. Okay? So that's a difference of 2. And if you think about it, if I try to use something similar to this many-to-many mapping to capture what's going on here, what should we do? Well, if you look at any entity from the employee entity set, and you look towards the department entity set, any employee can be manager of multiple departments. So from an employee entity point of view, it is a many mapping. On the department side, right? From the employee entity set point of view, it's a many mapping. But from a department entity point of view, it's a 1 mapping, right? Because you can only map to 1 employee entity. Does that make sense? Question? Okay. So this leads to a 1-to-many mapping instead of many-to-many mapping. The only thing remains is to capture these semantics in ER diagram. That's what we'll do.
When would you use an arrow in this case? Because are they both going the same, like both ways, when it's no arrows? Or is it when is an arrow necessary for like 1-to-many or many-to-many?
Yeah, that's exactly what I plan to discuss next. Good question, though. So, having understood those 2 cases, what's remaining to show is how to capture that in an ER diagram, right? Essentially the arrow question he just posed. The way you do that is the following. By default, when you use no error whatsoever, that indicates a many-to-many map, as demonstrated in that picture over there for the works in relationship set. That's a many-to-many map. When you have arrow though, that indicates one-to-many mapping. Specifically, the arrow you use the arrow coming out from the many side, Who is the many side on this managed relationship set? Well, the department is the entity set on the many side. Right? Look at going back to that example there. So you draw an arrow coming out from the many side, going towards the one side. On the other hand, the entity set on the one side, you do not use any arrow for it. You just use a line. And that indicates a one-to-many mapping. Okay? So you have to remember this particular representation. Huh? You have to remember this particular representation. So far so good? Okay, cool. So let me do a simple exercise. Right? Suppose if I may, okay. If I make this change, can someone tell me what does it mean? Okay? Can someone tell me what this means now? Yes.
Many employees to one department?
Many employees to one department. Yes, that's the literature meaning of it, right? What's the semantic of this? You know, if I ask you to translate this back to user requirement document.
Many employees manage one department.
Many employees manage one department. And? You only specify half of it, right?
Each department can have multiple managers, and each manager can have multiple employees under them, but each employee can only have one manager.
Drop the second part because it doesn't indicate from looking at this relationship only, it doesn't tell you whether one manager can have multiple employees under that. But combining the two, yes, that's implied because each department has multiple employees working for that. But looking at this just this one relationship that you don't have that second statement you have made. But by dropping that second statement, what he said is right. Let me repeat what he has said. Each department can have only one manager. Each department has multiple managers, but each employee can be manager of at most one department. Right? Because the one side is on the department now, the many side is on the employee entity set now. Does that make sense? Which means if we come back here, what that means is it's basically a flip of what's going on here. So you may have something like this. Right? You may have something like this. A department may have multiple managers, but an employee can be manager of only one department. Because it all becomes this. Okay? So that's just a simple exercise to help you further understand the constraint expressed by this particular diagram. Okay? Now, obviously we can also have one-to-one. For example, each department has one manager and each person, each employee can be manager of only one department. Does that make sense? That's a one-to-one mapping. And how do you express that? Well, simply use arrows on both ends. So if you were to do what it means is you can do something like this. So that's a one-to-one mapping. That basically means each department has one manager and each employee can be manager of only one department. So in a one-to-one mapping, this is no longer allowed. Right? This is no longer allowed. And you have to remove either this line or this line. Okay? Okay, so far so good. However, there's still one thing that's fairly important that's not captured by the discussion so far, which is, okay, you can have one-to-many, many-to-one, you can have many-to-many, you can have one-to-one. What if I want to express the following semantic, which is, an employee can be manager of multiple departments, and department can have one manager, but must have one manager. But must have one manager. Okay? So this is to go back to our earlier example. That's this example here. So let me go back to all the way back to what we start with. Okay, imagine the line is down instead of me wasting time on this. Okay, imagine that the line is coming down all the way. So going back to the original setup, the one-to-many mapping. What's not captured by this, though, is the following. Okay, we are back to one-to-many. So employee can be manager of multiple departments. So this is fine. Right? So let's suppose that's the setup. That's a one-to-many mapping. That's okay. But what if you want to capture the following, which is every department must have one manager. Every department must have one manager. So in this case, Department B does not satisfy the requirement because the Department B does not have a manager. But that's not captured by our design, by this particular ER diagram, right? How do you capture that? How do you capture that? Or to give you another example, even in this many-to-many mapping, assuming I want to have the following requirement, that an employee may work for multiple departments and a department may have multiple employees working in that department, but at the same time, every employee must work in at least one department. You cannot have employees who do not belong to any department whatsoever. Obviously, it doesn't capture, this will no longer satisfy the requirement I have specified just now, right? Because you have 3 employees who have no departments they work for. However, yes, they do not violate this many-to-many mapping, because many-to-many mapping says you can have multiple interactions with entities on the other side, but you don't have to. Right? You don't have to. Like, I can take multiple classes, but I don't have to. I don't have to take no class at all if I want to. So how do you enforce that constraint? This is something called total participation, right? In other words, so suppose I want to enforce this. So note that all departments must have a manager. Or coming on this side, all employees must work for a department. Note that there's a subtle difference between forcing this as a constraint versus it happened to be the case. What do I mean by that? Looking at this example, the user specification says all employees must work for at least one department. Henceforth, every employee entity must connect it to a line going to a department. That's what I mean by forcing a constraint, right? Forcing this constraint. At the same time, it happened to be, in this particular case I set up, it happened to be that all departments have employees working for them. But that's different from saying there is a constraint that every department must have at least one employee working for that department. There's a subtle difference, right? The difference is, if there are no constraints saying that every department must have an employee working for that department, I can add another department, and without employee working for that, that's totally fine. However, if it's given as a constraint that all employees must work for a department, if you add another employee to the employee entity set, you must assign a department that employee works for. So that's the difference between having a constraint versus it happened to be the case. Question over there.
Does total constrain both sides? So does that mean, so with the employee in the department, does that mean that every department must also have an employee?
No, that's your question actually relates to the two cases I mentioned, right? One is forcing a constraint versus it happened to be, right? So in other words, total participation constraint doesn't have to be on both sides, right? So the next question is, how do you express that in your ER diagram? Right? How do you express that total participation constraint in ER diagram? It's fairly simple. What you do is you use a both line on the side that you want to enforce that total participation constraint. For example, if this is the case, and I want to force this constraint, it's not just it happened to be the case. Rather, I want to force this constraint that all employees work for a department. What I do? In my ER diagram, I will change the line on the employee side with a both line. Okay? If I do this on both ends, that would mean this is no longer valid, because you have a department who have no employee working for that department. If I'm forcing this constraint on both sides, then you, then you must assign an employee to that department in order to satisfy your design constraint. Okay? You may wonder where all this constraint come from. Right? Where all this constraint come from? Well, they come from user specifications. Right? It doesn't come from you, the database application developers. It comes from your user requirement document, meaning whoever hires you to do the job. They will tell you what are the constraints in their business organization. Okay? If I continue with this example, if I use both lines for that, can someone tell me what that indicates, what that implies?
Is it that every department must be managed by at least one employee?
Every department must manage by exactly one. Yes. Okay, that's right. So when you use this, first of all, it's a one-to-many mapping, right? It's a one-to-many mapping to begin with, one on this side and many on this side. What that means is each department may have one manager. That's when you do not have that total participation constraint. Now combining that with the total participation constraint, what that means is each department may have and must have one manager. Combining the two, that's exactly one manager.
Can there be multiple managers per department, or is it still just one?
Just one, right? Because you still need to satisfy the one-to-many mapping. So that's why it's exactly one. Okay? What if I ask this question, if I continue with this example, if I change this to okay, can someone tell me what this means?
It means that
Go ahead.
that there must be at least one employee that is a manager and one manager that is an employee?
Say again?
Or it means that there must be at least one employee that is a manager.
It means that there must be one employee acting as a manager. Well, but that's exactly one semantic we have discussed, right? Yeah?
It means that every employee must be a manager, and each department must have exactly one.
Exactly. Right? That's what it means.
Can you repeat what you said?
Okay, what that means is each department must have exactly one manager, and every employee must be a manager. Every employee must be a manager because you have total possibility constraint on the employee side. And this, what that further implies, but an employee can be manager of still, an employee can be manager of multiple departments. That constraint is still in place. It's just that every employee must be a manager. Okay? You had a question?
No, you just answered
Yeah.
it.
Okay. The one-to-many mapping still is in place. Okay?
Based on the other goal lines, doesn't every employee also have to work in at least one department?
Which both line?
Oh, the one with the employees to work in,
Uh-huh.
that means that they have to manage and work in the department in at least one?
Well, that doesn't violate each other, right?
Oh,
You,
oh,
no, it doesn't violate. Next, we're going to talk about binary versus ternary relationships. Right? So far, we focus on what we call binary relationships. Binary relationships refers to those relationships connect two entity sets. Connect two entity sets. But there are cases, excuse me. But there are cases where we need relationships that connect more than two entity sets. Let me give you a concrete example to demonstrate when it is needed. Right? So looking at this example, so suppose I have employees, and I have dependents, and I have healthcare policies. So what happened is, so using this particular, this is a ternary relationship set, right? What that means is employees. One employee may have multiple dependents. So there's a one-to-many mapping between employees and dependents. That's one-to-many here. Okay? One employee may have multiple dependents. Common sense, right? Wife and daughter, those are my dependents. And there is a many-to-many mapping between employees and policies, which is also understandable. I may purchase multiple healthcare policies, one for my dental, one for my family doctor practice. Right? So an employee may have multiple policies. That's totally okay. And the same policy may be purchased by multiple different employees. That's why there's a many-to-many mapping between employees and policies. Does that make sense? And there's no total participation constraint here, which indicates this must be before Obama time. Right? Now we have Obamacare, and there must be a total participation constraint. Follow me? No? Which might be repealed fairly soon, so who knows? Okay? So far, so good. Right? So this design satisfies what we need. And by the way, also, using this design is how the same policy may cover multiple dependents, which is fine. I purchase policy, the same policy cover all my dependents. Okay? So this design is perfect so far. So that's a ternary relationship set, connecting three entities. However, if I add some more constraints, this design may become ambiguous, right? If I may provide this additional requirement, which says each policy is owned by just one employee. Each policy is owned by just one employee. What it means is, okay, you're going to customize the design of your healthcare policy so that each employee purchase a specific policy designed for him or her. So it's owned only by that employee. Right? Suppose I want to capture that. How would you do that using this design? Well, using this design, the way you're going to capture that is what? Can someone tell me how would you do that? Each policy is owned by just one employee, but it didn't say anything about whether employee may have multiple policies, right? So in other words, the same employee may still have multiple policies. Yes, over there. Change the line from policy to cover with error, right? Yeah, fantastic. That's the right approach. You replace that with error. That means now it's a one-to-many between employees and policies, meaning the same employee may have multiple policies, but the same policy goes to only just one employee, right? However, because you're using a ternary relationship set design in this case, this leads to an ambiguity design or an unexpected constraint stemming off from your ER diagram, looking at policy and dependence. Now you have what? You have a one-to-one mapping between policies and dependence. Accidentally, that's not what you want, but unexpectedly it arises from your design. There is a one-to-one mapping between policy and dependence, which is wrong because I never specify that one policy can only cover one dependent. I still want one policy covering multiple dependents. Make sense? Yeah.
Can you go over that arrow one more time?
That's for one-to-many between employees and policies. One employee may have multiple policies. A policy cover only is given to only one employee. That's why it's one-to-many between the two. But because of that, because you are trying to accommodate this design requirement, you accidentally introduce an unexpected constraint between policy and dependence. That's one-to-one, which is not what you want. Right? And there's no way you can fix this in this particular design. So how would you go about fixing this? How would you go about fixing this? Well, rather than using a ternary relationship set, which it's impossible to fix this using a ternary relationship set. What we're going to do is to break up this into multiple binary relationship sets. In other words, what I will do is replace the design on top with two binary relationship sets. What that says is, okay, employee may purchase multiple policies, right? One-to-many, and the policy covers only one employee. I can even enforce a total participation constraint here. Why? Well, it actually naturally makes a lot of sense because if a policy is owned by only one employee, there's no point to keep around a policy that nobody is interested in. So every policy must be owned by an employee. So we have total participation constraint on the policy end. But since we're not forcing universal health care coverage, we do not have total participation constraint on the employee end, right, in this design. But the policy can still cover multiple dependents. And let's say I use total participation constraint here as well. You don't have to, you don't have to, but I'm just using it in this particular example. What that means is every dependent must be covered by a policy. Actually, it makes sense too. Why? Because from a company point of view, suppose this is a corporation database, you are only interested in keeping that dependent information if it's covered by the healthcare policy purchased by your employee. Otherwise, why would you care about the information about that dependent? In other words, every dependent must be covered by a policy in order for that dependent to make into your database. So that translates to that total participation constraint on the dependent's end. Okay? So this meets that requirement over there, and without introducing that ambiguity, the one-to-one mapping between policy and dependence. Okay? So it's a very subtle challenge, but this example illustrates to you that sometimes it's better to use binary relationship set rather than a ternary relationship set. However, if you look at this example, if you take this example to the extreme, you can make the following extreme argument, which is, do we really need ternary relationship set? Do we really need that? Or in other words, is it always the case that I can replace a design with a ternary relationship set using two binary relationship sets, like what I have done here? Is it always possible to do so? Right? So this is what we're going to look at next. So the answer is no. There are cases where you do need a ternary relationship set. So consider this particular example. Suppose I'm building a manufacturing database, right? I'm trying to capture the fact that I have multiple departments, they order parts through multiple different suppliers, and in the by the means of contract, right? So I sign a department sign a contract with a particular supplier for certain parts, which is this design right here. And a department may deal with multiple different suppliers, may order multiple different parts, and so the same supplier may supply multiple different parts and work with multiple different departments. That's why it's a always many-to-many mapping between the three entity sets. Does that make sense? And there are no total participation constraint either, right? So meaning the department doesn't have to sign any contract or need any particular part. A supplier doesn't have to participate in this relationship either. Okay? That's the design on top. Perfect. Suppose you try to do the trick we have just done, meaning replacing the ternary relationship set with multiple binary relationship sets. So you come up with a design right here. Okay, you say a department needs multiple parts, and the supplier can supply those parts, and department also deal with those suppliers. Are the two designs equivalent to each other? That's my question. Can someone tell me? Your answer should be yes or no, and with a why. Right? So first of all, tell me yes or no. No. Okay. Tell me why.
Because just because the department needs certain parts and they're dealing with the supplier that can supply those parts does not mean that the supplier is necessarily giving the department those parts.
That's exactly right. So if you look at this design, department needs a particular part, and the supplier supply that particular part. And at the same time, department also deal with that particular supplier. Even with all these facts, you still cannot be certain that the department is ordering that part through that particular supplier. It's still not binding, right? Which is different from the design on top. When you have a contract connecting all three entities, that for sure tells you the department ordered this particular part through this particular supplier. Right? Does that make sense? Okay. Yeah.
I don't think I really followed you. Can you say that?
Okay, let me give you an example. I teach database class. You take database class, right? But that doesn't mean you are taking database class from me. That's a simple, example that's similar to what I'm trying to illustrate using the example here. Huh? Does that make sense? All right. So the final, actually, this is the second to last component in ER diagram. So the next thing I'm going to talk about is what we call is a hierarchy. So all of you have taken some object-oriented programming language before, like Java or C++. So in object-oriented programming framework, there's something called inheritance. Right? Suppose you want to design a class that's called car, and then you further divide car into different categories, like SUV, sedan, and truck, right? They all belong to car, meaning they have some common properties. For example, they all have 4 wheels. They might have an engine, they might have a door. But in each subclass, subcategory, you have specific properties, right? A truck is different from a sedan and different from SUV. So you have common properties that go into what we call the parent class. Then you have subclass specific attributes go into the subclass or children class, right? So in object-oriented programming framework, what you do is you have a car class as a parent class, then you have sedan, truck, and SUV as 3 children classes. They all inherit or extend the parent class, which is the car class. Do we have something similar in ER diagram? The answer is yes. The reason for that is because we are trying to capture objects in real world, and objects in real world do have this inheritance relationship. So we do have something similar to that in ER diagram. That's called the ACE-A hierarchy. So looking at this example, suppose I have employees entity set. But for my corporation, I have 2 types of employees. One is those hourly employees, and I also have those contract employees. But hourly employees do not have contract with me. They work on and get paid on an hourly basis. Contract employee, on the other hand, has a long-term contract with me with benefit and so on and so forth. But they do have some common attributes, like I care about their SSN name and, for example, office lot, right? Which particular lot they are assigned to. But for hourly employee, I care about the wage I'm going to pay them and number of hours they have worked, which I do not care or I do not have to worry about for contract employee. Because for contract employee, all I need to remember probably is the contract ID or some other attributes specific to the contract. Does that make sense? So the way you capture that is to use this particular component in ER diagram. It's a triangle with the letter ACE-A inside the triangle to indicate that's an inheritance relationship between the parent entity set and the 2 children entity sets. What that means is every entity here have those attributes in addition to those attributes from the parent entity set. Okay, that's what it means.
Is there a difference between, so in this case, obviously, contract employees and hourly employees are subclasses of employees, but what prevents us from thinking that employees and contract employees are a subset of hourly employees? Are there just the way that the triangle is connected or something, or I mean just common sense and stuff?
Well, I guess I don't 100% follow what you're saying, but I think what you're talking about is the 2 constraints I'm going to talk about next, which is whether an employee is always either an hourly employee or contract employee, or can we have some other type of employees floating around? Or similarly, can an hourly employee be contract employee at the same time, or vice versa? Let me, you know what? Let me cover what I'm going to say next. Then let's revisit your questions whether that covered that. So using this design, one thing that's not clear from the design is, exactly what I have just said. Whether, all my employees are covered by these 2 types of employees. Meaning, if you are an employee for my corporation, either you are an hourly employee or a contract employee. You cannot be anything else. Versus another design where, yes, generally speaking, I have hourly employee and contract employees, but I also have another group of employees who I haven't figured out whether they want to be hourly employee or contract employee. But I know they are my employees. For example, the new hires. Right? For the first 3 months, do a rotation and figure out whether I want to offer them a contract or I offer them a hourly based job. But they are my employees nevertheless. There's a subtle difference between the 2, right? Does that make sense? You follow me? And this is something called the covering constraint. The covering constraint. I actually go keep knowledge. So let's look at this first. In other words, that every employee must be either hourly employee or contract employee. If the covering constraint is true, that means yes, every employee must be either hourly employee or contract employee, meaning the two children entity set together cover everything in the parent entity set. If the covering constraint is no, that means you don't have to be an hourly employee or contract employee. It could be a subset of your employees do not belong to either of those classes. Okay? So that's covering constraint. The way you indicate covering constraint is by adding an annotation to design, say covering constraint yes, covering constraint no, to your ER diagram. Right? To ER diagram. The other constraint is called overlap constraint. Meaning, can an employee belong to two subclasses at the same time? Meaning, can an employee be hourly employee and contract employee at the same time? It might sound a little bit weird, but it does happen in practice, right? For example, I have a contract with my company, but from time to time, in addition to my contract job, I also want to do hourly job for the company. That happens, right? In some organizations, that happens. You have a contract, but in addition to that, if you want to work overtime or take on some side project, I'm going to assign you on an hourly basis. So you are both contract employee and hourly employee, right? So in that case, that's what we call overlapping constraint. If overlapping constraint is yes, that means you allow things like that to happen, meaning an employee can be hourly employee and a contract employee. If overlapping constraint is no, it means you do not allow that to happen. You are either an hourly employee or contract employee, you cannot be both at the same time. With that being said, take some questions over there.
Are overlapping constraints and covering restraints usually mutually exclusive?
No, you can have one of the two or both of them at the same time.
Okay.
They are not mutually exclusive.
I know it doesn't apply to this consideration, but what if allowing an overlap constraint meant that you couldn't have a covering constraint? Does that?
No, it doesn't mean that, right? Overlapping constraint doesn't only means that whether you can be hourly employee or contract employee at the same time. It doesn't say anything whether you can have employees who are neither of the both.
Okay.
Right? So you can use them in combination. Yeah, question at the back.
I think this is kind of going back to the question that the guy from had.
Okay.
How do you know which of the three entity sets is the parent class and which of the other two are the
I see. Is that what you're saying? Oh, the one on top, obviously.
Sure, yeah.
I see what you're saying. Top is a relative term, right? So, yeah, top, left and right, top. But typically, top is well defined. Sure. Of course, first is wrong, right? So, you never know. Right now. Yeah. Any other questions?
How do you show the overlap constraint?
You add an annotation to you that say overlapping constraint, yes, overlapping constraint, no. Similarly as you did for covering constraint. Okay. All right. Finally, the last thing I'm going to talk about is something called aggregation. So there are cases where you want to introduce relationship set. You want to introduce relationship between an entity set and another relationship set rather than another entity set. So what do I mean by that? So far, if you think about the design so far, we have talked about, a relationship set can only be introduced between two or more entity sets, right? All right? You cannot have design like this, meaning you cannot have and this is not allowed, right? You cannot have a relationship set connecting an entity set with a relationship set. It doesn't make any sense in our design so far. Right? But there are cases where you do want to do something like this. I'll give you an example, right? Suppose I have a regular ER diagram at the bottom. I have projects, I have departments. And departments sponsor certain projects, right? So department has some annual budget they can use to sponsor projects of their interest. So that's what's going on. Very simple design, right? Many to many. I can sponsor multiple projects, and the same project may be jointly sponsored by multiple departments. Very, very, very simple, basic, rudimentary design. But whenever money is involved, as we know, whenever money is involved, people are nervous, right? Whenever money is change hand is you are nervous, right? So what you want to do is you want to assign somebody to audit that transaction, that interaction, making sure every dollar is well spent, right? Like university has auditors, state government has auditors. They send to public university to audit us all the time to make sure the budget allocated to each department is well spent, there's no waste, and so on and so forth. So you want to have that relationship. So you have an employee who wants to monitor this sponsorship interaction, right? But here comes the dilemma, right? Here comes the dilemma. This employee or auditors, they are not auditing the department per se. Because I don't care, how many students you have in your department and so on and so forth. I only care about this sponsorship relationship that you have. They're not auditing the product per se, right? Like what's accomplished in the product, what are the research content, what are the activities of the product. Rather, they're really monitoring this interaction as a whole between department and product, right? That makes sense? So how do you, and that's basically like this, right? But ER prevents you from doing this, right? How do you do this? Well, ER introduced a particular component called aggregation. The way you do that is you introduce a dotted box that surrounds the whole relationship set and involving participating entity set. And what it does is to give you what we call a conceptual entity set. It's a conceptual entity set that encapsulates the entity set and the relationship that they participate in. Now with this conceptual entity set, now you can introduce a relationship set connecting another entity set with this conceptual entity set. And still be okay. That's essentially the design illustrating this background. Okay? Alright, that's everything you need to know about that. We're done. Okay? So a quick review of what we discussed and a couple of points to note just before I move on to the next part of the lecture. ER design can quickly get very tricky. So you're facing some of the tough challenges, like should a concept be modeled as an entity or attribute? I'll give you an example of that. So suppose I have a design like on top, right? This is entity versus attribute. Let's see whether, okay, entity versus attribute is this one, okay? What do I mean by that? Suppose you have address and you have employee entity set, and you want to capture the address information for the employee. Right? For every employee, I want to know his or her address. Naturally, that leads to the following design, which is very natural design. However, if I give you a little bit more information about user requirements, right? So the user said the following. Okay, yes, I want to capture the address for each employee. But note that I want to do the following. I don't want to keep store the address just as a string attribute. I do care about the structure within an address back. Meaning I do care about the street, the city, the state, the number, and zip code. You can, of course, treat it just as a string. But that's like taking an unstructured approach. Right? It's unstructured. You have to do parsing later on to figure out, which is the street, which is the city, which is the country, which is the state. Sounds like an easy task, but actually it's not. Right? Georgia is a country or state. Like, this is for real. I was in Florida when Russia invaded Georgia, the country. I was in Florida, right? Florida, north part of Florida. So I got radio signal from Georgia, the state of Georgia. A woman actually calls in to the news program So how come Russia invaded our state? And I don't know. I didn't see any Russian soldiers. That's the real story. For real, Russia invaded Georgia in I think around 2010, 9, right? So that tells you the structured information is actually important. You cannot just simply rely on parsing, because parsing can give you ambiguities in cases like that. Like Athens. Is that Athens in Greece or Athens in Georgia? Again, Georgia has a town called Athens. You know, if you are traveling, you want to know which Athens you are going to, right? If it's Athens in Greece, fantastic, pack your stuff. Athens in Georgia, you know, apply for sick leave and go. Seriously. So parsing is no offense to people from Georgia, by the way. I do like Atlanta a lot. You know, that's a perfect example, right? So you want to capture that. If you care about that structured information, and furthermore, let's say, of course, you can argue, okay, if I care about that structured information, fine, I'm going to do the following. I'm going to replace address with then I have a bunch of other attributes for the employee, like name and so on. Does this design work? Yes, it works, but it's a very archaic approach, right? Because for two reasons. One is you're introducing too many attributes for the employee entity set. And secondly, with this design, you are duplicating a lot of information. Right? Suppose you have 1 million employees from a particular city, then that city value will be duplicated 1 million times, for example, right? That makes sense? Right? Or, in another way to understand it, if you have multiple employees resides at the same address, because it's a apartment building, then you are storing that same address information multiple times, one for each employee. So a better design, if you care about that structured information within address, and you know that it's possible that multiple employees share the same address value, a better design is to, instead of treating address as an attribute, you introduce address as an entity with its own attributes, like cities, street, and so on and so forth. And you can now you can introduce a relationship set between the two. This also enables you to do things otherwise impossible with address being an attribute, like the employee may have multiple addresses. You know, I have 2 houses, 3, 4. You know? So with address being an attribute, you cannot do that. But with address being an entity set, you can do that. But it doesn't always mean this is the better design. If you don't care about the structured information within the address value, and your employees, for the most part, do not reside on the same address value, then this design, meaning treating address as an entity set, works, but it complicates the design. I'd rather treat address as the attributes in the latter case. Right? So that's the example. So here's another example. Okay. So suppose I have, this is a little bit trickier than the example I mentioned earlier. So employee works for departments. And I want to capture from when to when you work for a particular department. Fairly simple. I introduce 2 attributes to the working relationship, from and to. From and to. Huh? But what's not captured by that design, is the following. So I should have made this animation. So, what's not captured by the design on top is the following, which is, if you have a design like that on top, which is this, what's going on is, if I look at any one relationship from this working relationship set, I can have 2 attributes, from and to, right? Does that make sense? However, what I'm not able to capture is the fact that what if one employee works for the same department multiple times at different durations. So I was in Department A from January 1 to March 1st. Then I rotate to Department B. Then later on, I come back to Department A. to the first department I work for. How do you capture that using this design? Well, note that a relationship set allows only a single relationship connecting the same two entities. In other words, if you have a work-seeing relationship set, and there already exists a relationship connecting this entity and this entity, you cannot have another entity from the same entity set, from the same relationship set, connecting the two same entities one more time. You cannot do that. There's only one interaction allowed per relationship set for the same entities. You may ask, what about, okay, there's a relationship here, what about this? That's okay because they are from different relationship sets, even though connecting the same entities, but they are from different relationship sets. That's okay. But for the same relationship set, you cannot have multiple relationships connecting the same entities multiple times. They can only be connected once using the same relationship set. In other words, you cannot introduce another line here to capture the second duration. You cannot do that. So how do you fix this problem? The way you fix that is to use the design at bottom. You basically, what you do is you change the duration as an entity set instead of attributes attached to that relationship set. Now you can have a ternary relationship between employee and department and duration. So let me illustrate using this example here. What that means is, actually, I think, actually for the, to make it easy for the camera to capture, I will use the whiteboard here, I think. Because that way, can you guys capture the screen and whiteboard at the same time? So that you don't have to rotate the camera angle all the time.
It'll be small to see though, so we'll have to zoom and stuff anyway.
You gotta zoom in, okay. Yeah. A lot of work, right? Well, that actually shows the potential of computer science. Using artificial intelligence and machine learning, I can totally imagine a scenario where you zoom in the camera and adjust the angle automatically. It's doable, right? You do a computer vision segment to segment of me, the human body. That allows you to move the angle a little bit. Then by adjusting the font size, you can zoom in, zoom out. Capstone for that. All right. I'm serious. One of you can do it, right? Now, employee. So no, this is not what I want. So you have employees. Departments. So I have this employee working for this department. Using this new design, what I'm able to do is I have another entity on top that I can connect to, forming a ternary relationship between this employee, this department, and this duration. This entity has two attributes, from and to. Now, this design allows me to do this. I'm connecting the same two entities. However, I'm connecting to a different duration entity to indicate that this employee works for the same department but for a different duration. Does that make sense? And this is another example where, okay, that's enough discussion for entity versus attribute, right? Whether you should design something as entity or attribute. What about entity versus relationship? So look at this example, right? So I have this design. So employees manage a department. And being a manager of a department, I give you some power, right? Because if you don't give me any power, what's the benefit of becoming a manager? So the power I give you is, I give you a budget, right? I give you a budget, say you can manage this department with this much budget. I give you a separate budget for each department you manage. That's what this design tells you, right? Does that make sense? So there's a clear separation between budgets from all the departments you manage, right? Suppose I manage two departments, I will have two separate budgets. I cannot move money from one to another because they are attached to that relationship, that managed relationship. Does that make sense? Look like an okay design, right? Fine. Now, if I want to change my requirement, what I tell you is I want a little bit more flexibility. I tell you, okay, Feifei, you're going to manage 2 departments. I want you to make sure both departments function as best as they can. For that purpose, I'm going to give you a total budget, but I'm not going to tell you how you're going to spend your money on Department A versus Department B. If at the end of the year you feel Department B needs a little bit more operating budget, you can move money around. As long as the total spending from the 2 does not exceed the initial budget I allocated. Does that make sense? So it's a more flexible approach than this approach. And this approach doesn't allow you to do that because the budget is already separated into 2, and each is attached to a managed relationship between you and the department you manage. Does that make sense? So how would you do the things I described just now? Well, you have to use a different design. Instead of attaching that budget as an attribute to the relationship set, you treated that as entities instead of relationship set. You treat it as an entity set instead of a relationship. What you do is you say employee is manager for something called managed appointment. And it's a one-to-many mapping. It's a one-to-many mapping. And each managed appointment has an ID and has a budget. And then each managed appointment actually manages multiple departments. There's one-to-many mapping between these 2. Okay? This actually is a super flexible design in the sense that you can actually have partitions among the departments you manage. And then you can allocate your budget that, according to the partition you have. For example, let's imagine I manage 4 departments, A, B, C, D. I'm manager of 4 departments. I can have actually 2 management appointments, one for Department 1 and 2, Department A and B, one for Department B, C and D. Or I can do partition differently. I can have 1 management appointment for Department A only, and another management appointment for Department B, C, D. Does that make sense? Then I, the employee, is connected with 2 management appointments, and each is connected with 1 or 2 or 3 departments. Using this particular design, it's super flexible. Or you can have only 1 management appointment, because it's one-to-many means that it can be one-to-one, by the way. Right? I can have multiple management appointments, but I don't have to. I can have only 1 management appointment. That's okay. And then this 1 management appointment covers all the departments I manage. So this is a super flexible design. Does that make sense? There are some other, here is examples. So this is the ER diagram. They use slightly different notations. But it's essentially they means one-to-many, many, those constraints we talked about. It looks pretty hairy and complicated, right? But note that this is only page 1 or 2. Right? And this is also a fairly out-of-date design from Department of Interior Bureau of Land Management. And for real applications, sometimes it's even more complicated than this. So there are some summaries you can go over on your own. So let's move on to the next one. So we have learned ER model, right? And the next thing is relational model. Database systems do not understand diagrams. If you submit an ER diagram, actually, how do I phrase this? Well, they do not understand a diagram directly. Okay, you submit a ER diagram to a commercial database engine. Many commercial database engines actually do support ER diagram as a design tool. But inside that kernel box, the kernel doesn't understand picture or graph, right? What happens is that picture representation is translated into another model that's actually understood by the engine, right? So that translation, that particular model, that ER diagram will be translated into is called the relational model. It's called the relational model. So in practice, some of you may have database experience before, right? You might have built database application before. In a lot of cases, people jump to relational model directly without going through the ER design phase, which is okay as long as you're fairly certain about what you're getting into. Because ER model, in my opinion, is a very clean and concise way of capturing user requirements. And then it allows you to translate your design into relational model. But sometimes people go directly into relational model, meaning go directly to design tables and so on and so forth. The downside of that is, because you didn't go through a proper user requirement analysis phase using ER, you may end up with a design that's fairly bad. Even though you are able to capture all the information, but it comes with all different problems, which I will highlight later on. But in order to understand this discussion, we first need to understand that model, that relational model that people use. Either you design your database directly with relational model, or you start with ER diagram and convert into relational model. Either way, you have to understand this thing called relational model. And that's what we're going to cover next. Here is a quick review of database system, which I have done already, so I can skip now. So we talked about this before. This student example, I used this example at the beginning of the ER lecture to motivate you the importance of the data modeling process, right? But coming back to this example, this is essentially a relational model. Very simple, but that's essentially a relational model. Relational model often, many people view relational model as just a bunch of tables. In a nutshell, that's right, but there are many intricate concepts going behind those tables. That's essentially what we're going to talk about next. Okay. So why study relational model? Because relational model is the building block for structured data for relational database management systems. I talk about the difference between structured data, semi-structured data, and unstructured data, right? So I'm going to skip this slide. And relational model is a building block for managing structured data. So here comes the formal definition of relational model. Okay? Relational model, the definition is actually fairly straightforward, right? You're going to have relations, and each relation is nothing else but a table. And the table has two parts. One is called the instance. The other is called the schema. Let me give you a concrete example. So in this case, this is my schema. This part, the 3 records, is my instance. Okay, relational model basically says you're going to have multiple relations. This is one relation. You can have multiple such relations. Each relation has its own schema, which is fixed, and a particular instance. And the instance of a particular relation may change from time to time, depending on what records you have inserted or deleted from that relation. But the schema is fixed, given a design online. Of course, there are ways you can alter your schema, but typically you do not do that. If you have done a good design, you start with the schema, you stay with that schema for a particular relation. Okay? So the instance is easy to understand, right? Those are the records going to a particular relation. What are the schemas? So the schema basically specifies the name of the relation and the name and type of each attribute in that relation. Name and type of each attribute in that relation. So you can think of a relation as a set of rows or records or tuples. Right? These are all interchangeable concepts. Rows, records, tuples. They all refer to these guys. Okay? So for example, this is the schema of the student relation. Why? Because it specifies, first of all, the name of the relation, which is students. It also specifies the name and type of each attribute in that relation. Right? For example, the name of the first attribute is SID, type is string, so on and so forth. So that's the schema of the relation. You might have noticed that in this particular example, in the schema part, I show only the name but not the type, right? This doesn't mean type is not important. It's just that to simplify my drawing, I omit the type information from the design, which is oftentimes the type is self-indicative from the instance down below, right? For example, this obviously is either a string or integer. This is a string, this is a string, this is an integer, this is a floating number, right? So those are the types. The type of attribute basically specify, using the terminology, the domain of the attribute. In other words, what are the possible values that attribute may take? What are the possible values that attribute may take? And cardinality and arity are basically terminology people are used to describe certain statistical information about your relation. For example, cardinality refers to the number of records, the arity refers to the number of attributes you have. So those are just some terminology you just need to remember. One thing that's important for the relational model is all rows or all records or all tuples must be distinct. In other words, you do not, this is actually fairly easy to understand. You don't want to store the same object twice in your database, right? The same student record, you don't want to duplicate that twice. Why you want to do that? It's redundant information, and it makes it update much harder than it's supposed to be. Why? If you store, for example, a student record 10 times, and if you want to update the student age value, you have to update 10 times now instead of only one time. Because you have to maintain consistent values for all of the records. So there's no point whatsoever to store the same record multiple times. So a fundamental requirement in relational model design is that all rows must be distinct. In other words, all records or all tuples must be distinct. But this is not to say all values in each column of a relation instance must be distinct. These are two different concepts. What do I mean by that? Well, taking the name column as an example, you can have students with the same name value. For example, you can have two students named Smith. That's totally fine. But you cannot have two student records that are identical, meaning not only their name are the same, login are the same, age are the same, DP are the same, the SID are the same. That's not allowed. Okay? But it's okay to have duplicate values on certain columns of your relation instance, as long as you have no duplicate records. Okay? So later on, we will formalize this requirement that no records are duplicate of each other. Right? Fundamentally, this is captured by a particular constraint called the key constraint. Right? Just like in ER design, you choose one attribute as the key of your entity set. Right? So similarly, you want to use some attribute as the key of your relation, so that all other attributes may have duplicate values, but not on the key attributes. Actually, I'm going to stop right here, because the next is the overview SQL, which is slightly different from the concept we're discussing. So I will release homework 1 later today or tomorrow. You cannot work on all components of homework 1 yet, because some of it depends on the understanding of relation model and the relationship between ER and the relation model. However, you can start working on the ER design part of homework 1.